Today, we will discuss the Chapter 6 about experimental research. Experimental research is the most rigorous of all research methods and is arguably the best method for testing cause and effect relationships. Causality. Simply stated, causality suggests that a single event, the cause, always leads to another single event, the effect. Anderson states, causes and consequences concentrate on the relationships between phenomena, how one phenomenon affects another. In the social sciences, at least, the focus is normally on a variety of determining factors, which increase the probability of a certain event occurring, rather than on a single factor. Yet at least an understanding of causality is essential to the proper testing of causal hypotheses or relationships, and is useful in designing research studies to be as rigorous as possible. The conditions for causality. A necessary condition is one that must occur if the phenomenon of which it is a cause is to occur. That is to say, if X, the independent variable, is a necessary condition of Y. A sufficient condition is one that is always followed by the phenomenon which it causes. In other words, if X is a sufficient condition of Y, then whenever X occurs, Y will always occur. A condition may or may not be both necessary and sufficient for the occurrence of a phenomenon. One type of condition that can be considered, in addition to necessary and sufficient conditions, is the contributory condition. Bases for inferring causal relationships. One type of evidence for inferring a causal relationship is known as concomitant variation. Evidence of concomitant variation, or covariation when there are two variables, indicates that the independent variable X and the dependent variable or assumed effect Y. In the case of a hypothesis that predicts that the independent variable is a contributory condition of the dependent variable, the logical consequence next is controlling the variables. Certain characteristics or capabilities are essential to the experimentalische method. Virtually all quantitative research requires the measurement of variables, but experimental research necessitates the control and manipulation of certain variables as well. One of the difficulties in exerting adequate control in an experiment relates to the fact that there typically are a variety of extraneous independent variables that conceivably are influencing. Extraneous variables can also influence both the independent and the dependent variables, and thus create a spurious association between them. If the subjects are not completely equivalent going into the experiment, the extraneous variables may be controlled statistically during the analysis stage. However, this approach is less reliable than others, as it is done ex post facto or after the experiment. Random assignment. The third and best technique for equating two or more groups before the experimental treatment begins is referred to as random assignment or randomization, not to be confused with random sampling. It involves randomly assigning the subjects in the total sample to the experimental and comparison groups. Internal validity. Briefly defined, internal validity refers to the possibility that the conclusions drawn from experimental results may not accurately reflect what went on in the experiment itself. Generally speaking, the greater the control the experimenter has over the experiment, including the extraneous variables, the greater the internal validity. The greater the control, however, the more artificial or unnatural is the setting, and the lower the external validity. There are 8 threats to internal validity. 1. History, or specific events, in addition to the experimental treatment or variable, which occur between measurements of the dependent variable. 2. Maturation, or processes within the subjects operating as a function of time, such as growing older or more mature. 3. Testing, or the effects of taking a test upon the scores of a subsequent testing. In a library instruction experiment, students would tend to doubter on a second test of library skills. 4. Instrumentation, or the process wherein changes in the techniques used for the measurements or changes in the persons making the measurements affect a second set of measurements or observations. 5. Statistical regression. This is especially significant where groups have been selected on the basis of their extreme scores. 6. Biases in differential selection of subjects for the comparison groups. IFA researcher selected students for the comparison group, the group not receiving any library instruction. 7. Experimental mortality, or the differential loss of subjects from the comparison group. If during the course of an experiment, students who tended to be infrequent library users, perhaps because of the area of study. 8. Interaction of selection and other sources of invalidity. The results of interaction can be mistaken for the effects of the experimental variable. Those are the 8 threats to internal validity. Next is external validity. External validity is important because it relates to the possibility that conclusions drawn from experimental results may not be generalizable to the real world. Threats to external validity. 1. The reactive or interactive effect of testing. This occurs when a pretest increases or decreases the subject's sensitivity or responsiveness to the experimental variable, and thus makes the results unrepresentative of the general. 2. The interaction effects of selection, biases, and the experimental variable. It simply means that one must be careful not to select experimental subjects who are likely to be more receptive to the experimental variable than is the general population. 3. The reactive effects of the experimental arrangements can prevent their searcher from being able to generalize about the effect of the experimental variable on persons exposed to it. 4. Multiple treatment interference may occur whenever more than only experimental treatment is applied to the same subjects. Because the effects of prior treatments do not entirely disappear. Next topic is experimental designs. In spite of the challenges associated with creating equivalent groups, controlling for the threats to internal and external validity, and establishing adequate control over the experimental setting, experimental research holds significant potential for the resolution of library-related problems. As was indicated earlier, a variety of designs can be employed for experimental research, and the stronger they are, the better they can minimize or control various threats to internal. True experimental designs. 1. The pretest post-test control group design. One of the classic true experimental designs is usually referred to as the pretest post-test control group design. As will be seen after a few examples, the standard names of basic designs tend to describe them rather well, but diagrams point out their major features even more clearly. The diagram for this design appears as follows. In this illustration, and in the others to follow, the X symbolizes the experimental treatment or independent variable or cause. 2. The Solomon 4 group design. A second standard true experimental design is referred to as the Solomon 4 group design. It is diagrammed as follows. As can be seen, this design involves 4 randomly assigned, or equivalent groups, 2 of which receive the experimental treatment, and 2 of which are given post-test only. 3. The post-test only control group design. The post-test only control group design diagrams the same as the last 2 groups of the Solomon 4 group design and appears as follows. This design is not used as frequently as it deserves to be, perhaps because of its lack of a pretest. 4. Factorial designs. Factorial designs can deal with 2 or more independent variables and 1 dependent variable. As can be seen in the following example, a factorial design contains every possible combination of the independent variable. A simpler factorial design is as follows. Next is true experiments and correlational studies. Having discussed the essential criteria for true experimental research, and having looked at a few examples of true experimental designs, essentially true experiments can be conducted in real-life settings, assuming the controls are adequate. Such experiments are often referred to as field experiments. Difficulties to be avoided. In order to design an experiment that will be as reliable and valid as possible, the researcher should attempt to avoid the following. 1. Relying too heavily on a single experiment. 2. Using poorly designed or faulty data collection instruments. 3. Not identifying all of the variables that may affect the results. 4. Not choosing subjects that are as representative of the population as possible. 5. Introducing experimenter bias. 6. Introducing subject bias. 7. Making the subjects aware of the hypothesis being tested through unconscious signaling or behavior. And lastly, 8. Using an insufficient number of subjects. Evaluating the experiment. In evaluating the design and results of an experiment, there are several points that the researcher should consider. 1. The experiment should have the ability to test a null hypothesis, which suggests that there is no relationship between the variables being studied. 2. The experiment should be sensitive. That is, it should be able to detect relatively small effects or differences. In evaluating the results of the experiment, the researcher should assess the reliability of the data and its external validity, or generalizability. Pre-experimental designs. If random assignment of subjects in laboratory-like control are not possible, it will be necessary for the researcher to use a pre-experimental or a quasi-experimental design. A few examples of pre-experimental designs follow. 1. The one-shot case study. The one-shot case study, which can be diagrammed simply as XO, is an extremely weak design. 2. The one-group pretest post-test design. The one-group pretest post-test design presents a slight improvement over the one-shot case study because it incorporates a pretest or one more observation point. 3. The static group comparison. Another pre-experimental design, which improves a bit more on the preceding designs, known as the static group comparison, diagrams as follows. As can be seen, this design utilizes two groups rather than one, each if which is observed once. Quasi-experimental designs. Quasi-experimental designs usually include naturally occurring RUPs, but they often involve more than one group, and typically have more observation points than do pre-experimental designs. A few examples of quasi-experimental designs follow. 1. The time series design. The time series design is an example of a single-group quasi-experimental design. It takes this form. As a comparison will reveal, this design represents an extension of the one-group pretest post-test design O1x02. 2. The equivalent time samples design. This type of design is particularly useful where the effect of the experimental treatment is expected to be of transient or reversible character, e.g., library instruction, environmental conditions. 3. The pretest post-test non-equivalent control group design. This multiple group design has some of the features of the static group comparison and the one-group pretest post-test design. The comparison group would be selected for its similarity to the experimental group. However, its major advantage over the static group comparison is that one can measure pre-existing differences between the groups. 4. The multiple time series design. Second multiple group quasi-experimental design is the multiple time series design. It is the multiple group counterpart of the time series design and could be diagrammed thus. Assuming that the groups were exposed to the same historical conditions, this design should control for the effects of history. Ex post facto designs. Ex post facto designs represent a weaker type of quasi-experimental design. They are designed to simulate real experimentation by using a static group type comparison, such as to accomplish a pre-X equation of groups by matching on pre-X characteristics after the members of the groups have experienced the experimental variable. And the last topic for the chapter 6 is web-based experiments. Web-based or internet-based experiments are becoming more common, especially in some of the social sciences. This technique allows researchers to collect large amounts of data from widely dispersed people and locations at minimal cost. Summary: experimental research is generally considered to be the most rigorous of the basic research methods. Unlike historical and survey methods, experimental research is considered capable of supporting. Those are the topic being tucked in chapter 6, wherein experimental research. Thank you for watching. I hope this video can help you understand more about what experimental research is.